So in terms of this overview, again, we'll do a bit of background, the models that are within AGWA, some basic data requirements, go over some examples of watershed assessments with AGWA, talk just a little bit about modeling expectations, and I'd like to acknowledge all the major groups that have been involved with the development of AGWA that are listed below. So AGWA is an automated GIS interface for watershed modeling, and that includes hydrology, erosion, and water quality for the SWOT model. And it's designed specifically for resource managers and not necessarily modeling specialists. It's applicable to both gauged and ungauged basins. It operates with nationally available, US nationally available data, DEM, soils, and land cover. And we can use it to investigate the impacts of land cover change. So we can identify areas that might be at risk from flooding or erosion, let's say after a modification or urbanization. And again, we can look at the impacts of things like urbanization, fire, different mulch practices. And it provides repeatable results for relative change analysis. And we'll talk more about what that means. And this is sort of dependent on the data you have and its quality in terms of trying to make a quantitative assessment versus a relative change assessment. And again, you need very good rainfall and runoff observations to make a quality quantitative predictions. There's 3 established models within AGWA. The Kinross 2 is a watershed model. REM is a rangeland hydrology and erosion model that really forms the engine, if you will, for hill slope erosion and infiltration within Kinross. And then again, SWOT is a slightly more empirically based model, but that is widely used. And we do have quite a good user base, and these numbers I think are a bit out of date that you see on the right, but we continue to grow our database or our user base. In terms of the models, we have 2 distributed hydrologic models to address multiple scales. SWOT's typically applied at larger scales. It's applied typically at daily time steps for both monthly and seasonal assessments. SWOT does now have the ability to go down to hourly, I believe. It uses a hydrologic response unit or HRU concept and curve numbers to determine what is the partition between rainfall going into infiltration and runoff. Kinross 2 is typically applied to small and medium-sized basin. It has a dynamically adjustable, it does it on its own for sub-hourly time steps. It routes water in such a way that there's infiltration interaction. At the same time, there's runoff, run-on, as well as sediment transport. And it allows the explicit treatment of different cover and management types. In other words, you can put a physical, location that's say for a urban development within the context of the basin configuration, whereas SWOT with an HRU concept, let's say different properties such as infiltration will be averaged in to the things around it within the HRU. And again, our primary endpoints are runoff, erosion, sediment, and then nitrogen and phosphorus and SWOT. And the SWOT abstraction on the left doesn't make a distinction. So if this is a headwater basin, number 71, a channel, and then the contributing areas to the channel, doesn't make a distinction between left and right side of channel. And they actually use sort of a pseudo channel in 71 to mimic the effects of flow concentration. Whereas Kinneros and REM, we do make a distinction between the left and the right side of the channel, as well as the channel itself. So again, we've got flow routing directions, 72 and 73 into the channel, 71 into the headwaters of the channel. So our conceptual design and workflow of AGWA is illustrated in this slide. So we need to start by building the necessary GIS databases. And again, we'll go into all of these steps in more detail in the tutorials. Then we need to discretize the watershed into watershed modeling elements that we see here. And that's strictly based or as a function of topography. And then we want to characterize the model elements, and that's again done with things like slope for topography, soils, and land cover. So we're going to intersect these model element polygons here with the appropriate soils and the land cover. And after we do that intersection, we derive secondary parameters from lookup tables. Again, and these are things like infiltration, the saturated hydraulic conductivity, the sorptivity of the soils, as well as some of the erosion properties. With that, we build the input and run files and then subject it to either a user-defined storm, this could be a design storm, or actual observed data, and run the model. And any of the outputs that are listed in this table can then be brought back into the GIS and displayed spatially. And those are done with an automatic color ramp. And again, this allows you to quite easily identify spatially where there might be important or at-risk areas of erosion or runoff flooding. So in terms of basic data requirements, digital elevation data is, we typically use 10-meter data that's available nationally in the US. We can use other resolutions. 30 meters will typically be fine for larger areas in Western terrains. LiDAR can be used if it's available for a very intensive look. Soils data, we use USDA StatsGo, Surgo where available, as well as internationally we use FAO soils. Land use can come from several sources. NLCD, that's the National Land Cover Data Set. REGAP or GAP, Landfire is another one. And again, the weather or driving data might be a design storm, and there are NOAA 14, which we automatically query, can be used for small watersheds or point area reduction ratios. Again, observed rainfall, if you have it, and then we can also ingest National Weather Service radar rainfall estimates. And management information, again, is about, where and what management was done. And that's where you as the user or the person with the local knowledge can say, this area burned, it was a high burn severity, or this area was urbanized with more impervious area. And again, you can put those specific things into the watershed model after discretization if you need to. In terms of visualization of results, one feature that many users like is that we can do multiple simulation runs for a given watershed. So let's say you have the base case, you've got your base watershed data, run the model with a design storm, and then we can impose our management. So, again, in this case, we're looking at urbanization. So we save all of the results, both spatially and in time, from the first simulation. We can run the second simulation, drive it with the same weather or storm inputs, and then we can difference those two. So again, this allows you again to more easily see what resulted from the management. So in this example, not only do we have the spatial representation, but we can also pull out the temporal variation for a given model element. And we've got a color ramp on the hill slope contributing areas, and then the thickness of the channels, the channel response or the difference in channel response is also shown in a color ramp and by a thickness in the water. And we can present this both as a percent change as well as just a straight quantitative difference from the two simulations. And here's just a few examples of some assessment cases. We can look at historical change, and that was done or applied. We've got papers out on both the San Pedro and watersheds contributing to the New York City water supply. And this is where you may go back and get Landsat data from 1990, let's say, and you compare that to current conditions. If we want to project into the future, we've also done work where an alternate future might be proposed when people say, well, we're going to develop along these highway corridors, and this is what we think the basin will look like in 30 years. So you can, again, compare the impacts from that projected or alternative future to the current time frame. And again, here are the endpoints that we can get out of AGWA. We can look again at individual stream segments or subcatchments for sedimentation or runoff, and then use it in a decision support context for assessments and, let's say, placement of better management practices, green infrastructure, etc. So here's an example in Sierra Vista, which is southeast from Tucson, and we've got changing land cover. So again, this is historical to a more current setting. Here's a Landsat image. These are the Huachuca Mountains. This is the Sierra Vista area. There's both a town and a military base there. And here's just a simple classification of the image. So we can see, we have urbanized areas here. Now we jump to 1997, and we can see there's been a big increase in the amount of urbanized area. And so, what did this do in terms of our hydrologic response? Well, we can do a multi-scale assessment. Start with SWOT, look at the bigger watershed that's contributing. So this is the San Pedro watershed up to the Charleston gauge here. And actually the upper portion of the San Pedro is in Mexico. So the US-Mexico border runs through about here. And we're going to drive the SWOT model, and we're going to look at by daily precipitation. We're going to look at the change in annual water yield from the 1997 minus the 1973 situation over a 10-year simulation period. So the darker the blue, the greater the increase in annual water yield. And if we then want to look at a subbasin in more detail, such as the one here in the red oval, we can rediscretize the watershed in a Kinneros model, and again, run a design storm or observed rainfall. And we can see again where the biggest responses are for runoff. And in this case, we've sort of got it overlaid with the classified imagery here. So the darker the blue, the more the runoff we have. And as we can see, pretty obviously, it corresponds to the area of highest development or urbanization. So modeling expectations, what do you need out of the model? And there's first, you can do experimentation with it. And again, you may just use design storms, or you can even, make up your own model input. And again, you're just trying to understand the processes. And if you're going to present these results, again, model verification is important. From a regulation standpoint, there's a higher standard, and you would like to have a high level of certainty in the model outputs. And you really do have a need for absolute values. In other words, if there's a regulatory requirement that the total suspended solid sediment is to meet a certain criteria, you need to have good model calibration and validation results. From a planning context, you can typically accept a higher level of uncertainty in the model outputs. And again, this, you might look at, more importantly, at trends. And again, thinking about relative change analysis, looking at before and after, or with and without a particular change or treatment. The tutorials are listed here. As Shay said, there's descriptions of each of these tutorials in the link at the bottom of the agenda. And again, you're open to pick and choose from these. And the first ones are really quite important in terms of, basically learning the steps. And this first tutorial will take you through the majority of the operations and the steps to run AGWA. And after that, you might want to pick, if you're a fire specialist, look at the bear process tutorial. And again, there's other land management situations, and those again are for you to pick and choose from. So, with that, I'll conclude. And again, the web pages, the main web page for AGWA is listed here. And again, you've got it on your agenda. And again, we have documentation, software, tutorials, publications, presentations made at other meetings. So I will let you go, ask any questions. And you can put those in the chat, or we'll take a minute or two now if you've got any questions.